Yes, here we go. I'm going to start my slideshow in a play from, uh, oh, sorry, that's the wrong one. Oh. Okay, can you hear me?
I can hear you.
Okay.
Don't see any slides yet.
Oh, you don't have my, sorry.
There we go. Yeah.
Can you
Perfect.
see?
Yeah.
See it now? Okay.
See you and hear you. Yeah.
Okay, good. Okay, ready. Now, I'm going to just start by saying how delighted and honored I am by this invitation to come over to your workshop to share some of my ideas on the philosophy of climate science. And I'm going to start today by reviewing a few basics about several ways that I see global and regional climate models, how they can and do gain evidential support. It's in the hour after this one, I'm going to discuss social values. And I set that aside for right now. The ways that climate models gain support include, in my view, model fit, variety of model fit, independent support for aspects of the model, as well as variety of evidence of various types and robustness. And I'm going to, oh, why is it not advancing?
Yeah, your slides are not moving.
Okay, we're going to try a different way. Okay. You've seen this picture a million times. I just wanted to remind you that there's no general theory of climate, and that that makes confirmation complicated because there's no way to assure that all the complicating factors affecting climate, some of which are shown in this slide, to take them into account and analytically calculate what the effects on climate change will be, either on global temperature, precipitation, wind, pressure change, or any other significant climate variable. So looking at the picture, you're reminded of the very many causal influences on, for example, heat contained and moved in the atmosphere. You see positive and negative effects of volcanoes, clouds, solar inputs, complicated effects of sea ice, and so on. And details about ice vegetation, soil and water vapor, and the absolutely ornate interconnectedness of systems are represented in both global and regional climate models, and these sets of equations are generally analytically unsolvable beyond the first dimensional ones, and are instead approached, as you know, through computer simulation modeling. Now, confirming simulation modeling can get tricky. And I view it as basically an instance of theory articulation and application in climate science and in the other sciences. The huge general circulation models are presented in a 3D grid, as you know, within which the equations are solved, but the process is smaller than any grid scale, are represented indirectly through parameters and parameterizations or mini models, like convection or cloud formation and ocean eddies. And so that's just a reminder of the background against which global and regional models like this can be evaluated empirically. Ron Geary, a philosopher of science, saw model confirmation this way. He said, such and such an identifiable real system, and in our case, it's going to be a specific aspect of the Earth's climate, is similar to a designated model, any climate model that you're looking at in indicated respect and degrees. And he also always related that to a purpose. So he said it's important to this approach that scientists use models to represent aspects of the world for specific purposes. And finally, in his more recent work, a couple of years after that, he said agents intend to use a model M to represent a part of the world, W for some purpose, P. That's also the view of my dissertation supervisor, Bas van Frassen, which he presented in book form in 2008. This view is very similar to Wendy Parker's later view that you might be more familiar with. Note that different parts of the model can be interpreted in different ways. For example, one aspect of the model may be interpreted more realistically or mechanistically, while another part may not have a corresponding structure or process in the real world at all. But before we consider directly how models are confirmed, I want to take a slight detour into a technical idea, namely what's called model validation. Validation is very similar to the idea of confirmation in philosophy of science, but it's more contextualized. Here's a simplified view or example of how validation often works in climate modeling. So if a model was constructed using a data set from 1900 to 1980, for example, and it was a model of global mean temperature, surface temperature, it might be tested for good fit or validated using a data set from 81 to 2010, which is independent. Additionally, the model would be tested using also independent data from 1860 to 99, and so on. So the climate scientists use a variety of statistical metrics for this testing, depending on the data set and the model. The key idea of model validation is that the model is tested using data that were not used in its construction, for example, to estimate its parameters. It's very important in testing climate models because big observational data sets are always used to help structure and build climate models and make them more accurate. These data sets cannot then also be used to test the models, and they're often accused of doing so. And in fact, sometimes they do that. But modelers are, of course, aware of this and have tested the models using independent data sets as a matter of course, including data sets from the deep past, which provide a very different context. This is actually very politically important because it's politically significant that the use of independent data sets like those used in model validation in this example has not stopped either philosophers or climate skeptics from criticizing the models for not being validated. For example, skeptics at the Marshall Institute for decades have claimed that no climate model has been scientifically validated. And these claims are then recycled in the US Congress in congressional hearings about climate science, global warming, and policy decisions about global warming. And, saying that no climate model has been scientifically validated, obviously that sounds really bad. Belief in ideas like this has helped bring movement on climate policies to a complete standstill in the US. And what it would take for a model to be validated for those skeptics is left unknown. Historian of science, Naomi Oreskes, and my co-author, noted many years ago that the problem with the notion of quote validation in modeling was that it seemed like a black and white issue. Either a model is validated or it's not. Whereas the real issue is whether the model had confirming evidence to support its predictions and assumptions, its general conformity with observational evidence, which is rather a matter of degree. And that's the approach that I take. But here the skeptics also have some major complaints. in a letter to, and this is an old letter to Canadian Prime Minister Stephen Harper. It had enormous influence. It was published in the Financial Times more than a decade ago, signed by 66 scientists of various specialties. And it included several climate specialists. They wrote, observational evidence does not support today's computer climate models. So there's little reason to trust model predictions of the future. This was especially significant because Canada had adopted policy changes based on the reports of climate scientists and the 2001 report of the IPCC, which did rely partly on climate model results, which have since been independently confirmed. These are just examples of the frequent concrete claim frequently heard in the halls of the US Congress that models are inaccurate and cannot model present or past climate. It's true that there are still some uncertainties with climate models, of course, especially with cloud presentation. But it's generally untrue that the models can't represent present or past climate. And today I'm going to give a review of the various different types of evidence that modelers use to support their models. And the most straightforward method of testing and confirming a model, and I'm going to talk about model confirmation, which comes by degrees from now on. Most straightforward way to confirm a model is to make a prediction and see if the observations match the prediction in relevant ways. It's just called model fit or sometimes statistical model fit. The simplest of these tests compare global mean temperature outcomes from the model against global mean temperature observations. And this has been going on for decades. In order to do this, temperature readings from thousands of land, ocean, and satellite readings from around the globe are placed into a grid structure like the model so that the grid from the model can be compared to the grid from the temperature readings. And that's what's going on here. This is Jerry Meal et al.'s pretty picture from NCAR. And note the good fit of the red line of the model, combining greenhouse gases and aerosol pollutants and natural causes, with the black line representing the observational record of actual global mean temperature. The contrast is with the blue line, which represents the theoretical pure natural forcings or causes without the greenhouse gas or aerosol pollution effects. So there's the natural forcings, here's the greenhouse and aerosol forcings. Taking this approach to models, I might say that on an instance of model fit confirms a hypothesis about the similarity in certain respects and degrees of a real system to this designated model, where the model is used to represent aspects of the world for specific purposes, such as explaining the cooling of the stratosphere over the late 20th century. More on this a bit later. This kind of good fit has been repeated by countless modeling groups using different models and types of models, or what I call model types, but with the same basic ideas about the causes of climate change. Now, there are many more ways of testing model fit beyond testing whether global climate models can predict mean global temperature accurately. For example, the climate scientists want to know whether the variation either within a year or across years predicted by a model conforms to observations, or whether other variables are also accurately predicted by the model at the same time as mean temperature. Gleckler et al., of course, established a beautiful set of metrics and a beautiful examination of this. I wasn't able to have time to lift their picture and give it to you in this variety of good and bad model fit picture. But these are examples of good model fit that show you the variety of evidence of good model fit all the way back in the IPCC. This is a chapter from the IPCC in 2007 on climate modeling, and edited by lead author Dave Randall. So there are many ways of testing models and getting a variety of evidence of good model fit across a variety of variables and parameters. So there are many more ways of testing model fit beyond testing global mean temperature. And model fit or skill is always measured by testing against data that were not used in model construction. So models show significant skill in representing also mean climate features, such as large-scale distributions of the other variables of precipitation, radiation, wind, and those things. Additionally, models can simulate patterns of variability, which is really a rather different sort of skill. And it's a different type of statistic than static goodness of fit for an annual average. So in this statistic, the model is compared to changes in the variable over seasons or months. And this then tells you that the global models can simulate patterns of variability, like the advance and retreat. Yeah. Oh, sorry. Yeah, as you see, like monsoon systems, storm tracks, and so on, rain belts. There's also a variety of evidence for models because they can be used to reproduce features of past climate and climate changes, such as the mid-Holocene warming of 6,000 years ago and the last glacial maximum of 21,000 years ago, both of which have specific spatial patterns across the globe as well. And that's taken to show that the forces represented in models can handle values outside the ranges encountered recently, which is a very important test of empirical adequacy for a model. And in an especially nice example of model fit from more than a decade ago, almost two actually, Ben Santer et al. Simulated changes in the height of the tropopause. That's the transition or boundary in the atmosphere that separates the lower atmosphere from the upper atmosphere. And the model results were a good match to the observed increase in tropopause height. What's interesting about this is, and here you can see the red line giving the model predictions for the situation with greenhouse gases and so forth, and the black line giving the observations. And there's a clear contrast between the observations and the blue line, which gives you, represents the predictions from natural forcings alone with no greenhouse gas input. This is not the sort of result that can be tuned or fed into the model ahead of time before testing, since information about the height of this boundary wasn't used in the development of these models. So tuning involves the calibration adjustment of the model parameters to produce a better fit with observations. And it's often objected by skeptics and also often objected by philosophers of science that models only fit the data because they've been tuned ahead of time to do so. So this is a very nice example to bring up for them. Then there are the fingerprint models often used for detection and attribution of causes. So they give fingerprints or profiles of what the atmosphere would look like if a given set of causes or conditions were in operation. So these so-called fingerprint studies, they compare observed changes with various potential causes and the natural internal variability of climate. And this is another Center study from a long time ago. So let's look again at this particular set of models. And I'm sure you've seen this before, but for instance, only natural causes such as natural variability in the sun here would give you all layers of the atmosphere to be heating up fairly evenly, right? In contrast, if the greenhouse gases were in operation, playing a major role in recent warming, we'd expect the stratosphere or upper layer to be cooling while the rest of the atmosphere is warming. Now, since the observational evidence does indicate that the stratosphere has been cooling, and over the past 2 to 5 decades, it's incompatible with the model under which the warming is due to solar radiation irradiance alone, and under which the stratosphere would be warming. So these fingerprint models provide a detailed spatial and temporal patterns of change, to which it's then possible to compare the observational data in detail in its spatial and temporal patterns. So this is the North Pole to the South Pole, and this is the surface to the outer edges of the atmosphere. And by comparing the aerosol and greenhouse, here's aerosol, the greenhouse gases and the ozone patterns of responses in the atmosphere, they can be distinguished, they can be confirmed independently in an issue I'll say more about in a minute. But the pursuit of these fingerprint studies has obviously led to numerous investigations that demonstrate the empirical confirmation of the global climate models of ocean heat, glacial length, sea ice, and water vapor content, for example, all in which the greenhouse effect is the key forcing related to the observed changes. So fingerprint models thus play a significant role when thinking of gathering the overall empirical support for global climate models. And finally, we get to another kind of support. And it's important to see this is a very different type of support from the success of the models in prediction. It is rather providing independent evidence for the framework or assumptions of the model, in a sense, before the model is ever used to make any predictions. In climate models, the physical laws are supported through the other physical sciences and their applications, such as the black body emission curve and the formulae for the orbit of the Earth around the sun, used for calculating the incoming solar radiation. Thus, the basic equations and their forms are supported indirectly through the success of the physical sciences. But I'd like to mention a more direct form of support sustained by climate models that is also independent support for aspects of the models, which is direct independent support for parameter values. The independent support for aspects of the model or model type, climate models may be supported empirically through the experimental or observational support of parameters or parameterizations that I mentioned a moment ago. For example, these cloud parameterizations that are added to the models at scales smaller than the grid size can boost the support for the overall climate model through empirically verifying the details, say the droplet size or the upward internal flows of the cloud mini model. And I call the quote independent support for aspects of the model because such empirical support doesn't come from the confirmation of the projection or predictions of the entire model, but rather from a kind of sideways confirmation or support of the detailed parts of the model. Or you can take the representation of water vapor in a climate model. Water vapor is the most important greenhouse gas in a lot of cases. And positive feedback involving water vapor and temperature rise may be involved in increasing global warming as much as several degrees over the next century. So the US Department of Energy developed long ago the Atmospheric Radiation Measurement Program, launched in 1994 to help with understanding and modeling moisture and radiation processes. It uses highly instrumented measuring sites at land and ocean locations from the tropics to the Arctic to improve understanding and representation of atmospheric radiation and its interaction with clouds and water vapor. So the data from those instruments have subsequently been used for developing and testing models of varying complexity. And data like these from satellites from a similar project have more recently confirmed that the water vapor estimates used in the cloud models were in the right range. And these independent data provided independent support for the parameter values used in those models and mini models. So that type of confirmation of aspects of the global models is a particularly strong form, I think, of confirmation to complement cases of fit, which rely on the prediction of the model, since it anchors the model in the world completely independently from their success in prediction. So there's a very significant and also conventional manner of supporting climate models or any other scientific model, although it's rarely explicitly discussed, which is through a variety of evidence. And going back to our earlier case of model fit, a model is frequently strengthened by having a variety of cases of model fit, as we just saw, and as Linda Mearns and I argued at the AGU in 2011, actually. And it brings us to a yet further type of related support to models and model types, namely variety of independent support for aspects of the model. And this is perhaps the easiest to see from a picture. Here you see a model which I represent as a distinctive shape with a red causal core, that little red explosion, usually a greenhouse gas radiative causal core, which is in common to all these models, is a greenhouse gas radiative causal core. But there are also additional constraints imposed on the model, which are these parameters and parameterizations represented by the little arrows, such as cloud parameterizations and ocean mixing, for example. And you'll note that each model has a different set, a distinctive individual set of its own parameters and parameterization. This is a close-up of one of the models. And so we have a cloud parameterization, and here's some observational evidence, OE1, supporting that cloud parameterization independently from the model's success in predicting global mean temperature here. That's a prediction from the model of global mean temperature. And this is completely independent evidential support of the climate, of the cloud parameterization, which supports the structure of the model, right? And you have totally independent observational evidence supporting the ocean mixing parameterization. So as you see here, the more of these parameterizations and parameter values that are supported independently by their own set of empirical or theoretical support, the better supported is the overall climate model. And that includes support for the model core, which was, as you know, experimentally supported by Tyndall's own research from the 19th century. And this type of confirmation of different aspects of the model is a particularly strong form of confirmation to complement cases of good fit, which you get when this T estimation from the model is relatively accurate, which is a case of fit. It anchors the model to the world completely independently from their success in prediction. And I do insist that this is a very strong way to confirm climate models. And with that, I'll note another key point. Climate scientists usually see robustness as a reason to think models are better confirmed and more likely to represent real climate processes. And by robustness, generally, I'm referring to minimally the conversion of different distinct model predictions on a common result or range of results, such as a global mean surface temperature within a range, say, of 2 or 3 degrees Celsius, and the empirical support of those models. The fact that climate scientists usually see robustness as a reason to think their climate models are better confirmed and more likely to represent real climate processes was documented more than a decade ago by Zach Purtle et al. In a qualitative study of the contents of 6 leading climate journals since 1990. They found 118 articles in which the authors relied on a concept of agreement between climate models to inspire confidence in their results. I too defended robustness as an evidential strength of GCMs in earlier summaries of evidence. But philosophers of science usually do not consider robustness to be a confirmatory virtue. And by that, I mean a virtue that indicates a model is more likely to represent accurate or true claims. And here's a climate modeler expressing this same thought. Even if all models agreed perfectly with each other, this would not prove that they are right, said Yanni Raisinen. And it's a good argument. But I will describe a specific form of robustness, which I introduced, and I call it model robustness, that emphasizes empirical support of model components as well as their predictions or outcomes. And I show that this model robustness can, in fact, contrary to the usual philosophical convention, provide confirmatory evidence, which involves the application of a causal core of a given model type. A modeler in the 60s said that when there are multiple varying models of the same phenomenon in nature, like this, here they are, the shapes representing the variously differently structured models. The scientist often focuses on a common causal core, and sometimes I'm trying to get used to calling this causal focus, because it could be not greenhouse gas, it could be some other feature of the model, like its parameterization or something. Anyway, they could they could focus on the model, and regardless of the different idealizations or assumptions represented by the various colored arrows made in the different models, the shared red center here represents a real world phenomenon or cause under robustness. And so we can set up a very simple situation regarding robustness and inference. Climate scientists may think, when confronted with results such as this figure, where since a set of climate models here agree on a projection of temperature, global mean temperature, here, then we should simply have more confidence in that projection, right? At the very least, this is clearly a case of what philosopher Jim Woodward calls measurement robustness. And measurement robustness refers to using multiple channels to infer and converge on the correct value or range of values of a variable, or the reduction of error by repetition in independent contexts. You use different tools or methods to get a calculation. And Avogadro's number is the most familiar example of measurement robustness. And here's Avogadro's number calculated through 13 different independent methods, reckonings and experiments. They were used to establish Avogadro's number and the existence of molecules by Jean Perrin in the early 20th century as converging on A, or Avogadro's number, with the 13 independent methods, measurements, and experiments represented as distinct shapes. And Perrin established a robust convergence of measurements that was taken to be too implausible a coincidence not to reflect something about the real world. The key to the persuasiveness of the test case centered on the claim that the measurements were really from distinct and independent methods. This is the most common type of robustness assumed in philosophical discussions and also scientific ones. And it's also sometimes called heuristic robustness. And analogously, in order for reasoning about measurement robustness or a model version of measurement robustness to go through in climate science, the climate models under consideration need to be relatively and relevantly independent, as Reto Knuti and others have emphasized. But it seems clear that many climate models are simply variants of others and not genuinely independent in an important and meaningful way. So it's extremely important at this point to note that measurement robustness is usually used to aid the project of searching for a strong basis from which to use models to predict future climate variables. And for my purposes, robustness is most significant for its shoring up of causal accounts about past events, that is, for causal explanations. And for these purposes, I use this more complex picture of models based on a focus on the empirical support for assumptions of the models and the causal explanations that they can produce of a situation and good evidence. And this is important for this workshop because it's causal accounts and explanations that are uniquely offered by this storyline approach studied here. The contrasting attribution method of risk-based reasoning is not actually entitled to make singular causal claims, although they do produce them very frequently. As my co-authors Justin Donhauser and Party Paul and I note in a new paper, the risk-based authors acknowledge this technical limitation of their methods explicitly early on, but in 2005, but seem to have, with no counter-argument, dropped their acceptance of that limitation against causal claims and now produce them with abandon. We're going to talk more about this next hour. Well, it is model robustness that chiefly applies to the storyline approach, given its causal emphasis, and not significantly the other four kinds of robustness the philosophers and climate scientists talk about. And one of the chief consequences of this fact is that the requirement for some kind of model independence demanded by other forms of robustness, which, as many have commented, actual climate models don't have, is not required for model robustness. Rather, model robustness requires that the models be similar in important respects. They be from the same model family. So for the rest of this period, I'll use my interpretation of robustness that I call model robustness, that usually supports and indicates that the models correctly represent a real or adequate causal account in the climate system, a type that Woodward agrees is quite distinct from many of his other four defined types of robustness. And when we have convergence of key outcomes among distinct models of the same greenhouse gas model type here, as well as widespread empirical support for various aspects of these models, this is often seen as evidence in favor of the reasonably accurate representation of specific causal processes described in the models and represented here as the red causal structure. And note that I'm extending and transferring the focus on robustness from the product or the outcome of the models, which we just saw as the focus in measurement robustness, right, to a focus on the models themselves. Explicating this line of reasoning is useful not just for climate science and the application of storyline analyses, but for many types of scientific inquiry that now involve complex and computational models, including aspects of ecology, evolutionary biology, genomics, cog sci, engineering, design, physics, economics, and social sciences, and also likely for everyday reasoning that involves causal inferences. It's already been applied in economic modeling, in fact, in the literature. But very broadly speaking, we have ordinary robustness when we have multiple models all producing approximately the same result or prediction. And in climate science, 6 to a dozen or more, sometimes 20, 50 or more, 100 of these GCMs or system models are run on supercomputers, and then the model results or outcomes on specific variables are compared. Comparisons like this, especially the various MIPS, most famously the initial CMIPS, involving many GCMs, usually from many different countries, are prominent in the report from the UN's IPCC. And a clear example of ordinary robustness is that all of the available climate models that incorporate greenhouse gases as a cause of climate change produce an increase in global mean surface temperature in the late 20th century. And consider figure 1. This old but pretty graphic shows 14 different and distinct GCMs driving 58 separate simulations of 20th century surface global temperature trends. The graph shows simulations of global mean surface temperature anomalies over the course of the 20th century. And within the models, the changes in temperature are caused by both natural and human-made factors that influence climate, such as human causes like greenhouse gas and pollution, and natural causes like solar events or volcanoes. And the volcanoes represented by the vertical lines are important because they cool the atmosphere, of course. Each run of the model or simulation is represented by a thin yellow line in figure 1, and the model mean is represented by the thick red line. This mean model surface temperature anomaly is compared to the observational data represented by the jagged black line. The result of the modeling exercise include a good match, representing a clear increase in temperature over the century of about 0.8 degrees centigrade, just for the 20th century. And I want you to take a closer look at the variation in these models. A number of these thin yellow lines are multiple runs from the same model, started with different values for the parameters or variables. And the models from different modeling groups also vary in their assumptions and parameterizations, such as cloud cover or density, ozone changes, or changes in land use. Despite all this variation, they still have in common one vitally important thing, namely, they all represent greenhouse gases as a cause of the change in the warmth of the atmosphere. They're all the same greenhouse gas model type, where GG is the common causal focus or causal core of model type named MGG, or I just call it M for short. Actually, I've oversimplified with a comparison to this simple linear model. Just how accurate these greenhouse gas numbers are is a little hard to tell from a simple time graph of anomalies like this. And it's time to consider and go back and consider a more realistic and sophisticated view of what the evidence and models actually look like when considering global mean surface temperatures. And we can go back to the fingerprint models for that. And again, the different pictures show only one forcing or one cause in play, modeled, except the last one, which mixes all these causes together in the lower right. And they show not only temperature change, but spatial and temporal patterns, or temporal profiles. And we find that the evidence today shows a cooling stratosphere, a warming tropical troposphere, and other distinctive attributes of the effects of greenhouse gas effects. So let's call this bundle of observational evidence that matches this fingerprint model, TO, for temperature observations or profiles, where the temperature spatiotemporal profile predicted from the model type M is called TO, observational evidence of spatiotemporal profiles of predicted temperature from the models. In other words, TO include observational evidence of not just simple temperatures, but spatiotemporal patterns and profiles. And it provides profound evidence for greenhouse gas warming, a very different pattern of temperature profiles than models with no greenhouse effect. And that's a causal analysis, partly because of the fingerprint analysis. So today, the support for the greenhouse gas explanation for current ice temperatures comes from a variety of sources. And this is partly because it produces models with successful predictions and retrodictions time and time again against a range of independently confirmable and distinct background conditions, assumptions, parameterizations, and other model features. So let's explore this in a little bit more detail now. We start with the model type MGG. That's our greenhouse gas model type family, which has a greenhouse gas as a component in its causal focus, the red causal structure in the middle, robustly giving us increases in the global mean temperature T, remembering that this is now a spatiotemporally structured variable, not a simple line. Members of the family of model type M, namely, and here we represent M1, M2, M3, but it can go on to Mn, are each different. And they're represented here as different shapes, again, but all with the same greenhouse gas causal focus or core. So each of these models also has an array of different parameterizations, parameter values, and assumptions represent as A sub I. That's indexed assumptions, including parameterizations of cloud aspects like clouds, ocean mixing, convection, and also some values for different causes, and possibly different basic equations expressed in different formalizations for use in computer simulations. So for simplicity, let's take just a set of three distinct members of model type M, 1, 2, 3, all of which give us robust prediction T, and say that M1 contains certain assumptions and aspects of the model, including the small faint cloud parameterization 1 here, among other aspects, and ocean mixing 1 here, and model 2 contains cloud parameterization 2 here, and ocean mixing 2 here, and so on. So let's assume, and this is a plausible true to life assumption in climate modeling, that there is some clear experimental and or observational evidential support for each distinct cloud parameterization here, C1, C2, C3. And so we saw this before, individual model with observational evidence of each parameterization and causal core. So there is such evidence for that, and there is such evidence also, different evidence for these different parameterizations. And we've got here individual and separate observational support for cloud parameterization 2 and ocean mixing 2, even though these parameterizations are usually incompatible with cloud 1, as well as for each other ocean mixing parameterization, right? So this last assumption comes as a surprise to many philosophers, and it might even be a surprise to a couple of physicists, but it's extremely plausible in the climate science. And I would emphasize most that observations are incomplete, and there may not be enough observations to favor one of the versions of clouds above the others, although there's generally data supporting each version. Thus, we suppose different observations can support the distinct parameterizations, some of which may be incompatible. So note in both of these, we also have the experimental evidence supporting the model core here from experiments involving greenhouse gases done not just Tyndall, but since Tyndall. And moreover, the different AIs, all the different AIs, this arrow and all the other arrows, are each supported by their own bodies of empirical and theoretical evidence to all of the above reasons, even while they produce conflicting or contradictory climate systems. So let's consider our projections using our distinct greenhouse gas models, M1 through M3. We run the simulations using identical inputs of greenhouse gas levels. And let's say we obtain global mean surface temperatures and spatiotemporal patterns, T, for the present day or deeper recent past. The result is that we have a series of theoretical tests of distinct models with different parameterizations, but all including the same greenhouse gas causal factor. One thing we discover is that the model outcomes are constrained within some specific bounds, the same values. Thus, these are robust results amounting to a robust outcome. And now we test our T against temperature observations. And we discover, and remember, these are spatiotemporal profiles, and we discover that T is, to within our needs and purposes, accurate enough. So we have a small set of models, M1 to M3, that project T in an empirically adequate way, even though they use very different processes and AIs to do so. But one causal aspect of these processes is the same, namely the GG causal aspect, which we know experimentally ties greenhouse gas inputs to temperature outputs. And now we have sampled a variety of other processes in coordination with that causal factor, and no matter which ones we use with it, we still get T as an outcome. So let us summarize the situation. Models M1 to M3 all predicted T. T is multiply and robustly confirmed by observations, TO, of global mean temperature patterns. Also, consider the individual models. The individual model M1 is confirmed not just by its success in predicting T by TO, but also, crucially, by independent observational support for its parameterizations, and C1 and C2 and OM1, but also OE2, C2 and OE2, as well as experimental evidence for the causal core through laboratory experiments. There is, in other words, a variety of theoretical, observational, and experimental evidence supporting M1 using Geary's approach to models. This is short for model M1 represents well a specific aspect of the real world, say various structures of global mean temperatures to specified degrees for purposes X, Y, or Z. One benefit of multiple well-confirmed models is that we can test the causal focus or causal core in a variety of different contexts, which builds confidence in its efficacy and reality, and the fact that we are representing that causal focus and core accurately in our models. We find that the result is insensitive to changes in its assumption. That is, ceteris paribus, the cause of greenhouse warming works in the models, no matter what its surrounding model looks like in detail. We can also see this in the fingerprint models. But when we change the causal core assumption, that is, when we remove the greenhouse gas causal core, the model type is no longer empirically adequate, as we see in this blue non-greenhouse gas model type, where the model results are also on the face of it robust. The models agree with one another, but they also disagree with the observational record. Thus, when we take the overall radiative of models and intervene on their basic assumptions and core causal structure, we can produce causally effective or causally ineffective models. In addition, my model robustness focuses also on the empirical evidence for the model assumptions and parameterizations. We have different and sometimes conflicting empirical support for different ways that we can manipulate the GG model type, yet the model outputs remain the same, thus gaining us confidence in the applicability of the model type and its causal core. So my point is to emphasize that evidence supporting an array of inconsistent model assumptions can nevertheless be used to test claims about core causes. This gives more evidence and increased support of the robust explanation being pursued, so it is confirmatory, contrary to the claims of other philosophers. This diagram illustrates how three distinct models of the same type are capable of accurately and robustly predicting T across an array of distinct, incompatible, yet independently supported assumptions, as well as being well supported by other observational and experimental evidence. So in sum, one conclusion to highlight in this last segment is that my model robustness concerns the pragmatic and empirical virtues of the model type itself and its causal focus, and not mostly the repetition of the model outcome, commonly called robustness, although it uses this evidence. This is a big difference between my model robustness and all other sorts of robustness that have been delineated by both scientists and philosophers, which focus on the predictive model outcomes. The chief aim of model robustness is to confirm the adequacy or reality of the causal core of the model type, as well as confirming the model prediction itself. The crucial point of model robustness is that the confirmatory strength of the hypothesis involving the explanatory causal core, that is, involving greenhouse gases in our case, is boosted through its empiric in a variety of empirically successful models. In conclusion, the kind of model robustness I proposed and outlined in this section involves a specific type of reasoning, one requiring differences among a family of related but not fully independent models. This type of model robustness is a distinctive, common, and significant type of inference in climate science on my analysis. It uses a variety of empirically supported constructions of model components and assumptions to assemble an empirically solid model, and it adds shared and empirically supported model outcomes. All of this supplies confidence and realism to the explanatory applications of the causal core of the model type. So stepping back, today I've reviewed my analysis of an entire array of ways that climate models and claims about them may be empirically supported and confirmed, starting with simple fit, which may but does not have to be characterized by simple statistics of fit and goodness of fit. We moved on to varieties of fit, mentioning numerous cases of the kinds of fit that climate models can experience. We then considered a feature that I've been emphasizing about model confirmation since the early 1980s, namely evidence that supports the aspects and assumptions of the model, whether theoretical or empirical, and including parameterizations or mini models incorporated into the total model type of the model or model type that is independent from any success in model prediction. With this on board, it's clear that a variety of independent support for aspects of the model or model type is also itself more confirmatory the more there is of it. And finally, we considered the notion of model robustness that I introduced into the literature on climate model evaluation. And questions, comments, discussion.
Thanks very much, Lisa. Let me just see if there's any hands coming up. Or if people wish to just type something in the chat, that's fine as well. Maybe, Lisa, given we're on the hour, why don't we take a 5-minute break, and then people maybe see if there's any questions when we come back from that, and then how does that sound?
Yeah, good. I'll load up my other talk.
Yeah. Okay, so we'll take a 5-minute break, start at 5 past the hour.
Thanks.